Okay, we're back. We're back in the original venue. Somebody fixed the camera, so we're good. And it's going to be the last video lecture for chapter 2. It's going to be a real short one. It's just talking about radioactive dating. So radioactive decay can be used to obtain important data about the evolutionary history of life on Earth. You can actually find something that was once alive, and you can find out how old it is using what's called radiocarbon dating. Fossils are reliable chronological records of life. Yeah, they're reliable. As we'll see when we tackle the evolution chapter, we'll find out that they're very important evidence for evolution, but it's really incomplete. But they're reliable. It may be incomplete, but reliable. Fossils' age can be estimated by measuring the ratio of the two isotopes to learn how many half-life reductions have occurred since it died, and you can estimate the age of fossils and put them in an ordered sequence. We've been talking about the two isotopes of carbon that can be used to determine how old formerly living material is. Okay. First, so radiometric dating using something called carbon-14. Okay. Here's the thing. If you look at the back at the periodic table, you'll see that carbon's atomic weight is 12 point something. This is called carbon-12. And this is the usual, most common isotope of carbon is carbon-12, which means 6 protons, 6 neutrons. But there's another isotope of carbon called carbon-14 that has 6 protons and 8 neutrons. And here's the thing, carbon-12 is converted to carbon-14 at a regular rate in the very upper atmosphere, where there's like much more serious heavy radiation like gamma rays and X-rays. It converts carbon-12, so carbon dioxide in the atmosphere is mostly carbon-12, the carbon and carbon dioxide, small amount of it is carbon-14, and it's a particular ratio, and it's constant ratio. It's always the same. So, so while an animal's alive, and the carbon in the food that it eats is in the same ratio, always the same ratio, right? So when an organism is alive, it's always the same ratio. But carbon-14 will, once this organism dies, the carbon-14 in its body will decay into carbon-12. Those 2 neutrons will take off. This is the kind of radiation that's not dangerous. And it will decay into carbon-12 at a regular rate. It's called a half-life. I think it's like about 5,000 years. So after the organism dies, it has a certain ratio of carbon-12 to 14. And then and as time goes on, as I mentioned, the carbon-14 decays into carbon-12 at a constant rate. After I think it's 5,700 years, it's called the half-life. After 5,700 years, half of the carbon-14 will become carbon-12. So if you had a gram of carbon-14 in the body of this organism, after 5,700 years, there'd be half a gram. And then after 11,400 years, there'd be a quarter of a gram. Every 5,700 years, it drops by half. So what you do is you go to this formerly thing that used to be alive, that's not a fossil, and you look at the ratio between carbon-14 and carbon-12. You can tell how many half-lives have taken place. So you can tell how old it is. So you can date it. in thousands of years. And this is how, is that the end? Yeah. This is how you date things. And a good example of this is actually a human being. There was a body found. This was, I forget how long ago this was. It had to be at least over 20 years ago or so. That this body was found on the Austrian-Italian border. It was encased in ice, and the ice, the warming period, the ice melted, and these people. First, it was Italian. It was actually just barely on the Italian side of the border, but the Italian police found it first and thought it was just some guy who died when he was skiing or something, and they didn't want to do the paperwork, so they just left it. The Austrian cops come along, find it, bring it back. They realize it's different. It's not just a regular skier. This looks like it's pretty old. So they dated it by carbon dating. It turned out to be a 5,000-year-old body. And it wasn't completely decomposed because it was frozen for over 5,000 years. And they called him Utsi. And they learned a lot about ancient life here, that this guy had I think a copper axe. He had these mushrooms, and he had particular clothing. And it was interesting. It felt that he had some metal fragments in his hair, so I thought maybe that he was a metallurgist, and he actually made the axe in his care. Found all kinds of interesting information. And the Italians wanted them back. But the Austrians said, well, you had your first shot. But they eventually gave him back to the Italians anyway, and put him into a museum in Italy because he was actually on the Italian side. Anyway, so it provides fascinating input into ancient life on Earth. Okay, but carbon dating can only be used for a maximum of 50,000 years. If something's older than 50,000 years, you can't date it using carbon 14 because there's such a tiny amount of carbon 14 left after 50,000 years. It's like 10 half-lives. There's so little left that it's undetectable. So how is it that we know that a lot of fossils are older than that? For example, dinosaur fossils. They are 60, 70 million years old, and they know how old they are. But so they didn't use carbon 14, they used different isotopes. There are other isotopes of other elements that have a standard ratio, and they decayed at a regular rate also, and some of their half-lives are like millions and millions of years. So that's how they can use these other isotopes to determine the age of dinosaurs and trilobites and really old organisms. And even tell you, how old a rock is that the fossil is in. Well, that's how old a fossil is, how old a rock is. And so they've determined that the oldest fossils on Earth are in microscopic fossils in rocks that are 3.5 billion years old. So it looks like life first arose on Earth about 3.5 billion years ago. Before that, there were no, and the Earth is only about 4.5 billion years old. So it took about 1 billion years for life to have arisen on Earth. How it arose, nobody knows. But that's how long life has existed on Earth. Okay. So that's a little thing on radiometric dating, and it's interesting, and that's going to be it. So this is Bio 106 Chem 4, and that's the end of chapter 2. So we'll go on to chapter 3 in the next video lectures. So I'll see you later for now. Let me stop recording. Where is it?